Okay, so in our last video, we saw that if we needed to do a change of variables over some bounded region of f of x, y, dA over to the double integral over a new region, and we can call this new region S, of f of u v, we needed a conversion factor, and the conversion factor that we're going to use is the absolute value of our Jacobian, and then we will either do a du dv or a dv du. Okay, so the steps for actually doing this, and there are going to be some steps involved in this. The first thing that I would do would be to take my equation in x and y and convert it over to an equation of u and v, and we should be able to do that based on the substitutions we are given. The next thing we're going to do is we're going to find that Jacobian. Now, in order to do that, what we're going to need here is we need functions in the form x equal and y equal, because remember, this is going to be the determinant, and let's write this out here. This is going to be the determinant of the matrix, which has across the first row the partial of x with respect to u, partial of x with respect to v, then the partial of y with respect to u, partial of y with respect to v. So we need those functions to be in x equal, y equal format. And then finally, we will convert our bounds from xy bounds over to uv bounds. And for these, we actually are going to need a u equal and a v equal in order to make this work. So let's go ahead and do some examples here. On your first example, you're going to take the double integral over a bounded region R of x, y, dA, and use the conversion that x is equal to 1/2 u plus v, which is the same as 1/2 u plus 1/2 v. And y is equal to 1/2 u minus v, or 1/2 u minus 1/2 v. And R is going to be defined as the region bounded with the vertices 0, 1, 1, 2, 2, 1, and 1, 0. So let's go through the process. The first thing we're going to do is take our function of x and y and convert it over to a function of u and v. And this should not be too hard to do. Here is our function. We've got x times y, and we know exactly what x and y are equal to. So we can just do those substitutions in here. X is equal to 1/2 u plus 1/2 v. Y is equal to 1/2 u minus 1/2 v. So when I multiply this together, let's see, I'm going to get 1/4 u squared, the outer and the inner go away, minus 1/4 v squared. So this then is my new function. Okay, and so next I'm going to go ahead and calculate my Jacobian. And the Jacobian, remember, is going to be the determinant of the matrix, which has across the first row, and I should have circled this one here, the partial of x with respect to u, which is 1/2, partial of x with respect to v, which is 1/2. Across the second row, we're going to use the partial of y with respect to u, which is 1/2, and the partial of y with respect to v, which is a negative 1/2. And then, of course, we know we go in this direction and subtract what happens in the other direction. So we get a negative 1/4, and that's 1/2 times 1/2, minus 1/4, which is going to be a negative 2/2, or a negative 1/2, negative 2/4, excuse me, or a negative 1/2. And so we get our Jacobian. Now notice when we go to input it into our formula, we're going to be using the absolute value of that. So be aware of it. And then finally, the last thing that we need to do is we need to change our bounded region. Our bounded region is made up of the points in x and y. And those points look like 0, 1, and they're given to us right here in our problem. 1, 2, 2, 1. and 1, 0. And so we're going to need to convert those over to bounds of u and v. And in order to do this, I really need to have, instead of just an x equal equation and a y equal equation, I'm going to need a u equal and a v equal. And I believe I can find that from these. Matter of fact, I can just do a simple elimination here. If I take these two equations and I add them together, I get x plus y will be equal to u. So you see now I have an equation for u. 1/2 u plus 1/2 u gives me a single u. So now I know how to convert my u from x's and y's. How do I figure out how to convert my v's? Well, I'm just going to come in here and I'm going to put this back into one of these equations. So everywhere there's a u, I'm going to put in an x plus y. So I get x plus 1/2, x is equal to, if I look at the equation correctly, 1/2 times u, which is x plus y, plus 1/2 v. So I can solve this for v. X is equal to 1/2 x plus 1/2 y plus 1/2 v. Let's go ahead and move these two over to this side by subtracting. And I get 1/2 x minus 1/2 y is equal to 1/2 v, or v is simply equal to x minus y. So I have my two equations here. U is equal to x plus y, v is equal to x minus y, and I can go ahead and get my ordered pairs here. So I like to go through and do all the u's and all the v's so I don't mess it up. U is x plus y, so u is 0 plus 1, 1 plus 2, 2 plus 1, and 1 plus 0. And then y is v is x minus y, so 0 minus 1 is a negative 1. 1 minus 2 is a negative 1, 2 minus 1 is 1, and 1 minus 0 is 1. So we get our new integral here, meaning that we take our old integral, which looked like this one here, and we convert it to a new integral. And the new integral looks as follows. We're going to take our new function, xy, which was equal to 1/4 u squared minus 1/4 v squared times the absolute value of our Jacobian. And then I have a choice here whether I do this as a du dv or a dv du. I'm going to do this. Let's look at what it looks like first, I guess. That would make the most sense. Let's see what it looks like here by graphing out the points that we just got on a u and v chart. So let's see. I got the point 1, negative 1, 3, negative 1, 3, 1, and 1, 1. So what I get, well, that really works out quite nicely, doesn't it? So I can see what my bounds look like on here. So if I do this as a du dv, or you could do it the other way, u is going right to left. So as I come across from the right, I hit u equal 3, and I go all the way to u equal 1. And then the dv, grab the bounded region and bring it over to the v-axis, and I'm bound between negative 1 and positive 1. And so this is a very simple integration. Just multiply the 1/2 through and then do your double integration. And you might be asking at this point, why on earth would we go through and do this? Well, this is what our bounded region looks like in u and v. Let's go back for a minute and look at what that bounded region in x and y looked like. And if I look at that, remember the bounded region was composed of vertices having the ordered pairs 0, 1, 1, 2, 2, 1, and 1, 0. And so let's see, 1, 2, 2, 1. Okay, so I have 0, 1, I have 1, 2, I have 2, 1, and I have 1, 0. And so if you look at this in X and Y, this becomes a whole lot more difficult to integrate, doesn't it? Because no matter what I do, well, first off, there are 4 lines that make up this bounded region. There's the line here, and how do I figure out what that line is? Well, it goes through the ordered pairs 1, 1, and 1, 2, and so I find the slope and then determine what that line looks like. And then I have a line here. I have another line that makes this up, and I have another line that makes this up. And so if I decide to do this as a dy dx, I'm going to have 4 separate lines here. I'm going to have to split it down the middle because I have a different top and bottom here than I do here. If I decide to go side to side, I'm going to have to split it this way. And so what happens is I wind up having to come up with equations of 4 separate lines. And in addition to that, I have to do 2 sets of double integrals to do the same thing that I was able to do in one. So it may have been a little bit of work to change the bounds, but in terms of doing the integration itself, it's a whole lot better.